All right, welcome to section 6.2, and we're talking about hypothesis testing or hypothesis tests for one mean. And I said in module 5, we're going to kind of learn a process and then we're just going to run it over and over and over again. So I've kind of stripped down the steps here because we really are going to use the same steps. We're going to make a null and alternate hypothesis. Then we are going to draw a picture, figure out what our test statistic is. To do that, we need to find the standard error. Then we'll figure out a p-value, we'll make a decision, and then we'll have an interpretation. So for the t-distribution, we get a little change of pace with the standard error. It is the sample standard deviation divided by the square root of n, a change from what we had previously. And then our test statistic is really similar here, except for we have, last time we were doing p hat minus p because we were talking proportions. And now we have x bar minus mu, and then dividing by our standard error. Because we've switched distributions, we have a little bit different way for figuring out the the p-value from our test statistic. And so it depends on our left tail, right tail, and two-tail action. And sometimes I kind of bounce between just using the t-distribution right tail tends to work just the same way our normal standard dist works. So a lot of times I just kind of use that. Remember, you can kind of draw a picture here and highlight what it is that you know and then move towards the questions. So as it comes to questions here, our first one looks something like this in the work, excuse me. So historical data indicates that the mean weight of male runners in a marathon is 183 pounds. New research seems to indicate the mean is now not equal to 183 pounds. Express the null and alternate hypothesis in symbolic form. So we're talking about a mean here, so we have a change from p to mu. Our null hypothesis is always that something is something, and then here it says kind of historical data. That's sort of what our population is. Sometimes it says there's a claim, and we'll use that value here. Again, these are going to be our claimed values, and then new research seems to indicate that the mean is now not equal to 183 pounds. So we don't know if it's less than, greater than, or just different. But not equal is kind of nice in that we can choose the not equals. So we have that. And this is really one of our first steps. So now getting to a problem with some numbers here. You wish to test the following claim at the significance level of alpha equals 0.01. So I'm going to pop over here and just start listing some data that we have. I think I said 0.01, but it's actually 0.02. Not sure where that came from. Here we have the null and alternate hypothesis given to us, and the takeaway here is we're going to be dealing with a two-tailed test. Right, because we're not equal to. Remember, if the arrow goes to the left, we're left-tailed. If the arrow goes to the right, we're right-tailed. And if we're different than or not equal or something like that, we have this. Now we're given some information here in the next one. You believe the population is normally distributed, but do not know the standard deviation. You obtain a sample size of 23 with a mean. So a little different change in terminology here or symbolic work. I'm trying to clean all those up, but we're using a free platform, saving some money here. And so this is the mean. They tell us it's the mean. We call that x bar. And a standard deviation, that's S of 17.4. So again, as you're doing your work, it's kind of nice if you focus on telling me what it is you know, and then I can know that you know these things instead of having to interpret it when it comes to partial credit or understanding what you have versus what you intend to communicate. So the formula sheet, also super handy right here as we're coming into this stuff. So we can use that formula sheet. Now, I do want you to draw, and I'm going to use the mouse to draw because a lot of you probably don't have a stylus, so who knows how this will work out. Our t-distribution really kind of emulates the normal distribution, so I sort of keep up with the same thing here anyway. Now, a lot of times I do this after the test statistic, but we have some information here that can kind of help us. The mean is 71.1, so that's going to be here, and our sample one over here, 57.7, will be somewhere over here. So I don't know exactly what those values are. And if you don't want to try to draw them, you can sort of put some highlights on there. And then 71.1. Use the boxes here to kind of get some stuff. Now, if I get fancy here, maybe alignment. Maybe if I line these to the left, it'll look a little better. Just being a little extra, I could just drag my picture over. Oops. I want this to the left, and I actually want this to the left also, and they're a little closer. You can also just scribble those numbers in if you want to. Okay, so we've got a picture here. I forgot to put in the tail area. This is two-tailed, so we're going to have a tail here, and then it's going to get doubled over here. We don't know what the test score is, but somewhere over here there'll be another one. So because it's two-tailed, we got a little action to do. All right, so the standard error. We've got the information to find the standard error, and this stuff is on your formula sheet too. So it's S divided by the square root of N. And I'm just clicking on these cells. I know it makes it a little less readable, but it makes it precise. And then if we wanted to copy and paste it to do some others, we could. So we've got the standard error. Now we need to figure out what our test statistic is. I guess that's not abbreviated, but this is. So we need to add some parentheses. We'll have x minus x bar, which I didn't even write up here, excuse me, mu, 71.1. I probably should add that to my list of things there, and then we're dividing by the standard error. So probably could have added from the null and alternate hypothesis up there that we have mu 71.1. Should have added maybe even. So from what we know about distributions, we are 3.7 standard deviations to the left here. So this is probably way over here. We're probably looking at a pretty small tail area. So in finding that p-value, I have a couple options. The first one I'm going to do is just keeping it like we did with the normal distribution. I'm going to double the area to the left. So if I go here and do t distribution, this should return to me, it says x degrees of freedom and then cumulative here. So this is x. My degrees of freedom, I didn't list them up here, is actually n minus 1. And then true gets me the area to the left. So I'm doing this here. This is my test statistic. This is my degrees of freedom, which is n minus 1. And then true, that's the area to the left. And since this is two-tailed and I have a negative test statistic, I have to double it. So I'm getting my p-value now of this. And oops. Well, I replaced the equal sign. So if I just pop the equal sign back in there, it should, there we go. Round this to 4 decimal places. 1, 2, 3, 4. And then I make a comparison here. This is my p-value. This is my test statistic. And I get to make a decision. So let me enter these. The test statistic, negative 3.693, followed by a 3, 0.0013. Now, and I make a comparison of my p-value to alpha. I'm less than. And we reject the null hypothesis if we are less than. And that means that there is enough evidence to support that the mean is different than 71.1. We don't really have a context here for all of that. But there we go. We got it. So again, quick little recap. Get the important information listed here. I forgot mu. We'll use that. We need our alpha so we can compare it to our p-value. We'll use the standard deviation of the sample and the sample size to find our standard error. We'll take the difference of our test statistic, our sample mean minus mu, in parentheses, got to divide that by the standard error to get our test stat, and then appropriately using the right distribution here to figure out what we have there. So I'm going to come back and do a couple more examples